Hey everybody, today we're going to solve the design HashSet problem on LeetCode. So this problem is marked as an easy problem, and that's only because this is something that if you have a CS background or you've done some studies in data structures, this is something that'll be pretty familiar to you, or at least it should be. It might be something you haven't seen in a while. But if you look at this problem and say, well, I have no idea where to start, why is this an easy problem? That's okay, it just means you haven't seen it yet. So, hash sets, hash tables are arguably the most important data structure in computer science, and that is why problems like design hash set are very common. It's unlikely that you will be asked directly, hey, design a hash set in an interview, but well, it's unlikely. It's very possible that it may happen. Okay, that's because of how common and important a data structure a hash set is. Okay, and why it's so important is because a hash set or a hash table, those two terms are pretty much interchangeable and synonymous. In this case, we use hash set when we mean it's a literal set of things, and a table is usually used to describe storing key value pairs. But the reason it's so important is because it provides dictionary operations of insert, search, and delete in what's known as constant time. Okay, and in constant time, that means doing those operations does not depend on the number of items that you're storing. Okay, so if I said, hey, here's a list of numbers, I need you to figure out, I need you to store them and figure out if you have a certain number. Okay, the very naive way of doing that would be, hey, let's just keep a list of numbers, and every single time we want to know, do you have this number in your list of numbers? You would start at the beginning of the list and check every single number and see if it was in the list. Okay. What hash sets allow us to do, and that naive way of doing that would be considered a big O of n operation, because as your size of numbers that you're storing increases, your time to figure out if you have a number increases linearly. Okay, because you're checking every element. Hash sets allow us to do it in constant time, okay, and we'll talk about how that works. So our hash set needs to be able to add a value into the set, know if it contains a value, remove a value. And again, these will all be in constant time when we have this done. Example, they add 1 to the set, add 2 to the set, they check if it contains 3 true, 1 true, 3 false, adds 2, now again it's a set, so we don't have duplicates. So they add 2 twice, and then it just contains 2 is true, and then remove 2, and then it just contains again false. So it's a set, so it's only going to have one copy of that element. Okay. So here's a little code that I added at the top. Okay. This is a class called hash node. Okay. What we're going to do is we're going to store an array of hash nodes. Okay. Basically an array of linked lists. And the elements in this array will be hash nodes, basically the head of a linked list. And the hash node, just like any other linked list, has a pointer to the next node, and then the integer value that we're actually storing. Okay, so understanding that bit of code's, important for the problem. Again, we're going to be storing, what we'll actually be storing in our hash set class is an array of these hash nodes. And these hash nodes represent the heads of linked lists. Okay, so here's how this will work. Like I said, we're going to have an array of these hash nodes, a list of linked lists. Okay, or an array of linked lists might be an easier way to think about it. It would be simpler to explain this if I had another, visual way of showing you guys this. But here's how it works conceptually. We're going to have an array of linked lists, okay? And for each element that we're given to add to our list, we're going to compute a value that is an index into that array, okay? And for each element that we're given, that value that we compute will always be the same. So instead of checking the entire array for an element, when we get an element, all we have to do is compute this index called the hash or the hash value, and then check that index to see if it's there. We don't have to look at the whole array. So that's how we get constant time. Okay? Now, what can happen here is the size of our array is going to be smaller than the number of elements that can be stored in it. So obviously, 2 elements could end up with the same hash code. Now that is why it is an array of linked lists instead of just an array of booleans or array of integers. Okay? So we compute the index, and then we find that element. If there's nothing there, we'll just add a new hash node at that element, at that index of the array. If there's already something there, that's called a collision. Okay? It means 2 elements have the same index into the array. So what we will do is just add that new element into that linked list at that index. Okay? So here's how this will work. Here's our constructor for our hash set. We set our array up to be a new array list. Okay? We keep track of the size, which is the number of elements in the array, number of hash nodes that we've added. Now, I default this to having a length of 10. So, for the first 10 elements, I just add null. Okay? So, when it's constructed, we have an array of 10 null elements, of 10 empty linked lists. Alright, so this right here is a method that I wrote called getIndex given some key. And this is a simple way of doing this. This is what this is doing is computing a hash value. Now, hash codes, hash values are very important, so much so that every object in Java, and this will work in other programming languages as well, has a method that will compute a hash value for it. Okay, I've basically written my own very simple version of that here to show you how this works. So we want to figure out with this function a index into our array where we can put the specified key. Okay, so a very simple way of doing that is just doing the key modulo the array size. Okay, so let's say we start our array size at 10. There's 10 buckets, essentially, 10 indices where we can put these linked lists, and we're given the key 16. Okay, well, 16 is not an index into that array. Okay, an array of size 10 will have indices 0 through 9. So what we'll do is we'll take 16 modulo 10. Okay, which will give us a number in the range 0 to 9. Okay, that will get us into our allowed values for an index, and that's where we will put that specified value. Okay, if you don't really know how modular arithmetic works, look it up real quick. Just kind of Google how it works. Basically, by taking the modulo, you get the remainder after division. Okay, so 16 modulo 10 will return 6, because 16 divided by 10 was 1 with a remainder of 6. Okay, so it gives you the remainder, and by giving you the remainder after division of some number, you get a number within 0 to that number minus 1. Okay, so this is really important. There's a real simple way of computing a hash code. Again, there are way more sophisticated, better ways of doing this. They are all implemented in the language already. So there's no real need to do this. I just wrote this as a simple way of computing a hash function so you guys can understand how this works. We will compute the index that we need to put the element by just taking the modulo of the number of indices we have in our array. So that's how we guarantee that we find a spot in the array. Now here we are going to add a key into our hash set. Okay? Well, again, it is a set, so we need to avoid duplicates. So the first thing that we'll do is say if our set does not already contain the key. If it contains the key, we won't bother adding it. So if it is not contained, if it's not in our set, then what we'll do is this. We'll make a new hash node with that key. We'll then compute its hash value by calling that method we just talked about, getIndex of that key. So what that will return is a number from 0 to the array's length minus 1, giving us a valid index to place that element at. Now, all we'll do is put it into the head of the linked list at that index. So our new node's next is equal to whatever is currently at that index. It could be null, which means it's just the head of that linked list, or it could be whatever is already at the head. We'll just put our new element at the beginning of the list. We set the element at that index to this new node that we've created, and then we get the size. Okay? Now this right here is the most confusing part of all of this. This is the resizing of the hash table. Right? In order for this to work, in order for this to be fast, I should say, in order for this to be fast, then the size of our table has to grow as our indices are growing, as the number of elements we're storing is growing. If it doesn't, then we'll just end up, so let's say we just left this at a size of 10, and we stored 1,000,000 numbers in this table, and they were all of varied values, then we would end up with 10 really, really long lists of numbers, linked lists of numbers stored at these 10 indices, okay? And that would not be fast at all to search for an element, because we would just have to search those entire lists, and our actual time complexity would be on O of n again. In this case, just O of n over 10. In order to avoid that, what we do is we compute what's called the load factor. So this dot size, which we're keeping track of, which is the number of elements we've actually stored in the array, divided by the array size, which is the number of indices that we have in. When that grows to being greater than 0.7, now this is an arbitrary value, could really be anything, okay? 0.7, 0.75 is a pretty common number to use for this. So basically what that's saying is, if we have stored enough elements to where we are using 70% of the indices, okay? If we're nearing that threshold, or we go greater than 70%, then what we're going to do is double the size of the array, okay? So the way we do that is come up with a temp array, and we set that to our current one, and then we set our current one to a new array list, and then we just double the size. So for I is 0 up to the old size times 2, we just keep adding null, and then all we have to do is go through the old elements that are currently stored in that temp array, and we add each of those elements into the new one. So we loop through here. If that indice is not null, then we get the head of the list, and each element in that list we just add to our new array. Okay, this is this part in here in particular, the resizing of the table is probably the most confusing part of all of this. Okay, so add in general is fairly simple. All we do is, hey, does it contain it? If it's not already in there, then we create a new node, we generate its hash value, and we just put it at that index. Okay, so the adding, the resizing code, which I've highlighted here, is the most confusing part. So if that doesn't make a whole lot of sense, don't worry about it too much. Sort of get the key concepts down, and then come back to here and figure out this resizing portion. Now, while it is the most confusing part, it's also obviously vital. Like I said, if we didn't resize it, then this whole thing would be kind of pointless unless we started with an array of just massive length, which is a waste of space. Alright, so remove is fairly simple. So if we're going to remove a key, the first thing we're going to do, just like with add, we're going to see if it's in there. So if it contains it, then we're going to remove it. Okay. So we compute its hash, which again is the index in our array where it has to be. And then we're just going to loop through that linked list. And then at this point, all we're doing is removing an element from a linked list. So right here, we just find it. Okay. And then at the end, all we do is remove it. So if the previous is null, then that means that the element that we were looking for was the head of that linked list, so that the element at that index of the array just gets set to its next element. Else, it means it was somewhere else in the list, and we just cut it out by setting its previous next to its current next. And then we update the size because we took one out. And contains is simple. So a common theme here, we compute its hash. Again, that's the whole idea here. Using getIndex, we figure out the hash, which again is the index that it has to be at. Okay. In order for this key to be in our table, it has to be at this index that we compute. And all we do is, now all we're doing, once we figure out that index, we're just searching a linked list for an element. So the head of that linked list is going to be the element at that index in the array, and then we just search for it. While cur is not null and cur value is not equal to p, we just continue looking for the list. And then once we get down here, since we've broken out of this while loop, either cur is null, meaning we didn't find it, or its value is equal to the key and we found it. So we just return cur not equal to null. Alright, cool. So, slightly longer video, mainly because, again, this is probably the most important data structure ever. It's super important to know how they work. If you don't get asked it directly in an interview, it will be expected that you at least know how these work. And if you get asked, you can talk about how it actually works intelligently. Now, obviously, every language on the planet has an implementation of a hash table that you're going to use, and you're never going to write your own code to actually do it. But it is really important to know how this works behind the scenes. So I won't really go back through this pretty long video anyway. I won't really go back through and rehash any of that stuff. But I'll just scroll through the code and you can pause and take a look.